Welcome to the course on error control coding and introduction to convolutional code. So, in this lecture we are going to talk about performance bounds for convolutional codes. In particular, we are going to analyze the performance of Viterbi decoding, which is maximum likelihood decoding for convolutional code, and as an example we will consider a simple binary symmetric channel. Now, if you recall, what is a binary symmetric channel? So, there are two inputs 0 and 1, 0 and 1, and with some probability 1 minus p, we receive the bits correctly, and with a crossover probability of p, the bits get flipped. That is our binary symmetric channel. So, we are going to analyze the probability of error when we are doing Viterbi decoding of convolutional code over a binary symmetric channel. So, as an example, we will consider one particular convolutional code. In this case, we are considering a rate 1/3 convolutional code, which has memory 2. So, it is a 4-state convolutional code whose generator matrix is basically given by this. So, these are my generators 1 plus d, 1 plus d square, 1 plus d plus d square. And without loss of generality, we will assume that all 0 code word was transmitted. So, all 0 code word was transmitted over a binary symmetric channel, and we received the bit. We applied maximum likelihood decoding, Viterbi decoding, and now we are interested to characterize the performance of the Viterbi decoding algorithm. Now, we would require one more concept which we discussed in lecture 2C, which is input output weight enumerating function. So, what does input output weight enumerating function tells us? It tells us about what is the input that will cause, what is the corresponding output that it will cause, and what is the length of that particular sequence. So, as you can see, these all 0 paths through the trellis are all valid code words. So, this weight enumerating function essentially enumerates all non-zero code words. So, for this particular example, the input output weight enumerating function is given by this expression, and which we can expand, we can divide this by this. So, this we will get our terms. Now, here x is the exponent of x will give me the overall weight, the exponent of w will give me the information sequence weight, and this length will give me the length of this path, like of this. So, the time it diverges from all 0 state to the time it remerges at all 0 state. So, x7 WL3 means there exists a code word of distance 7, which has information weight 1, and the time it diverges from all 0 state to the time it merges back to all 0 state, that is 3, and there is one such code word. This can be interpreted as there is a code word of weight 8 and corresponding input weight is 2, and it has length 4. Length 4 meaning, again, by this L denotes. So, you have your code word which diverging from all 0 state, and then after staying in some non-zero state, it is merging back into your all 0 state. So, this L denotes the time from which it moves away from all 0 state to the time it takes to come back to all 0 state. So, let us talk about what do we mean by error here. So, since we considered an all 0 sequence, we expect that our correct path should be the one which goes through all 0 state, because our transmitted code sequence that we assumed, if you recall, we assumed that an all 0 code word was transmitted. So, what is the correct path? The correct path is one that goes through all 0 states. So, this is the correct path. Now, when will error happen? An error will happen if at a particular time instance, let us just say this is the time instance I am looking at. If at this time instance, instead of deciding for this path, if I go for this path, then error will happen. Why? Why is this an incorrect path? Why is this an incorrect path? This is an incorrect path because my transmitted code word was all 0 sequence. So, if I decide in favor of this path instead of this path, then I make an error. So, I say a first event error happens at some arbitrary time t if the all 0 path is eliminated in favor of a non-zero path, which is our incorrect path. So, the first instance when I do that, that is basically my event error, because I should have chosen all 0 path, but at this instance what happened was the metric corresponding to this path was better. So, I chose this and I eliminated this path, but this is a wrong path because my transmitted code word was all 0 sequence. Now, what does we know that all paths through this trellis are essentially valid code word. Now, what does this incorrect path does? It diverges from an all 0 state at some other time before this time t and has merged back into all 0 state at time t for the first time. So, that is what we call first error event. So, at a time t, when we are deciding in favor of some other path other than the all 0 path. So, that means this is the time when this other path, the incorrect path has merged into all 0 state. So, at some time in the past it would have diverged from all 0 state, and now at time t it is merging back into all 0 state. Now, can we find out what is the weight corresponding to this incorrect path? Yes, we can, because when we write the weight enumerating function of a convolutional code, it enumerates weight distribution of all valid code word. Now, any path through this trellis diagram is a valid code word. So, we can easily enumerate what is the code weight corresponding to any path through this trellis. Now, when will we decide in favor of this incorrect path and not the all 0 path? We can take this example of the same code that we are considering. Let us just, this code has d free 7, then it has one code word of weight 8, one code word of weight 9, there are two code words of weight 10, like that. So, minimum distance d free is 7 here. So, let us assume that this incorrect path had weight 7. Now, when will you decide in favor of this path rather than this path? When the number of errors are such that, when there are more than 4 errors such that your received sequence is closer to this sequence rather than this, right, then you will make an error. Or let us say if this path was weight 8, then of course, when your error is more than 4 bits, you will decide in favor of this path, and whenever error has happened in 4 bit location, there is an equal probability you can either choose this path or you can choose this path. So, we can calculate the probability of this first event error. we can find out its probability. What is this probability? Let us say this incorrect path has weight d. So, d is the weight of this incorrect path, which has diverged from all 0 state at some other time and has merged back at all 0 state at time t. Now, if d is odd, then this probability is given by sum of this probability, and where summation takes place over all error pattern which are greater than d plus 1 by 2 to up to d. So, in the example we just considered, let us say if we had an incorrect path of weight 7, then we should look at error pattern of 4, 5, 6 and 7. If 4 errors happened, maybe it will bring us closer to this incorrect path rather than all 0 path. Okay. Now, if P is the crossover probability of changing flipping of the bits. So, P times E will give us the probability that E number of bits have flipped, and 1 minus P raised to power d minus E will tell us the probability that d minus E bits have not flipped, and DC d choose E is number of possible combinations of in which we can have these error patterns, E error patterns among this set of d weight. So, this will give us the probability of first event error. Again, we will make a decision in favor of incorrect path if our receive sequence is closer to the incorrect path, and we know what is the maximum likelihood rule for binary symmetric channel. It is we choose a code word such that the Hamming distance between the received code word and this chosen code word is minimized. So, if there are 4 or more errors for the case when incorrect path has weight 7, then you are going to choose basically go for this incorrect path. What about when d is even? When d is even, for all error patterns from d by 2 plus 1 to d, you will decide in favor of incorrect path, and whenever the error is d by 2, then there is a 50-50 chance, because you can just then there is a tie in the matrix. So, you can just flip and choose either of the path, and that is why for d by 2 I have written here it is half times this probability plus all error patterns of weight more than d by 2. So, for example, in this case we had one path of weight 8, right. So, if our incorrect path was of weight 8, then all error patterns of 5, 6, 7, 8, they would have caused decision in favor of this incorrect path, and whenever there is an error pattern of weight 4, there is a 50-50 probability that I may choose an incorrect path or I may choose the all 0 path, because the Hamming distance is same from all 0 path or this incorrect path. So, that is why I have a half here. So, this is the probability of first event error. Now, if we are looking at time t, then all incorrect path lengths of length t or less can cause first event error. So, we would now use union bound to essentially upper bound this probability of first event error probability. So, what does union bound says? Probability of union of errors is basically upper bounded by union of probabilities of error. So, we are going to upper bound this first event error probability by sum of error probabilities of all these incorrect paths. Now, if we also allow incorrect path of any length even greater than t, then in that case the first event error probability can be upper bounded by this. So, this is the probability of first event error of weight d, and how many such weight d paths exist, that is given by this, and you sum over your d which goes from free distance of convolutional code to infinity. So, this will give you an upper bound on probability of first error event probability. Now, can we make use of the weight enumerating function of the convolutional code to calculate this, and this is what we are going to show. So, let us first try to simplify the expression for probability of first event error. So, this was the expression for first event error probability. So, let us try to simplify this expression. So, we will first do it for when d is odd, and then we will do it for when d is even. So, when d is odd, the expression is given by this. Now, note that this crossover probability is typically small. So, this is and again it is a number between 0 and 1. So, if you raise it by a higher number, you get a smaller quantity. So, the first upper bounding that we are doing is, instead of raising it to e, we are raising it to d by 2, and again because this is a number between 0 and 1, see the actual expression would have been this p raised to power d plus 1 by 2, then d plus 3 by 2 by 2, and like that it basically this number will go on decreasing because you are raising it to a higher value. Now, I can just fix, instead of varying it as fixed, I keep it fixed and I kept it as d by 2. So, that is the first upper bound that we are getting. Next, this term does not depend on e, so I can take this out. So, what I am left with is this d choose e, where e goes from d plus 1 by 2 to d. Now, next upper bounding what I did was I replaced it by e equal to 0. So, instead of e equal to d plus 1 by 2, I am adding more terms, I added from e equal to 0. So, that is why this upper bound came, and what is this? This is nothing but 2 raised to power d. So, then for odd d, I can write this first event error probability as upper bounded by this quantity. Next, let us do the same thing for even d. So, for an even d, the expression for first event error is given by this expression. So, first thing that I do was I upper bound this by changing this exponent from e by 2 plus 1 to e by 2. Note that in this expression, when the error pattern is d by 2, I considered a 50% probability of making an error. Now, I just removed that and I added that here. I removed that 50% thing here. So, that is why I am getting an upper bound here. Next, same as in previous expression, I replace p raised power e by p raised power d by 2. And again, because p is a number between 0 and 1, if you raise it to a higher number, it decreases. So, I just kept it at d by 2, which is the smallest value of e. Third thing which I do is, again like in for the odd case, this term does not depend on e. So, I can bring it out. So, I brought it out, and what I am left is with this, right, and then I add terms from E0 to up to d by 2. So, I replace this by this. So, again then I am upper bounding it because I am adding additional terms here. So, this quantity will be less than this quantity, and finally, this is 2 raised to power d. So, I get my expression for first event error probability for d being odd given by this expression. So, P d is upper bounded by this for when d is even, and we showed even for when d is odd, it is upper bounded by the same quantity. So, then what we can do is we can write that our first event error probability is upper bounded by this. We just showed this for d equal to odd and d equal to even separately. So, we can upper bound this probability by this. Now, what we are going to do is, we know our weight enumerating function. So, will give us the distribution. So, if we have some weight enumerating function, it essentially will give us from d equal to d free to infinity, it will give us how many code words of weight d are there, and x raised to power d. Okay. So, we are essentially making use of this weight enumerating function, and we look at the form of our first event error probability. So, looking at these two, we can write then that first event error probability can be computed from the weight enumerating function by replacing the weight, that x, by this quantity. So, this we obtain by comparing this equation with this equation. Okay. Now, what sorts of error events can happen? So, let us just spend some time on that. What type of error events can happen? So, of course, you can have a scenario where you have multiple error events. So, you diverged from all 0 state, you merged back, then you again diverged, you merged back, you diverged, you merged back. This can happen. Now, when will you? So, if your decoded path is this, that means the metric that you are getting here is better than the metric value for all 0 state, and that is why you are deciding in favor of this. Now, there are multiple ways in which these errors can happen. So, error events can happen in multiple ways. So, let us say there might be a situation when you have diverged from all 0 state and then merged back into all 0 state, and then after some time you again diverge from all 0 state, stay away from all 0 state, and then you merge back, and again then you stay away from all 0 state, diverge, and then again merge back. So, you can have multiple error events happening. Now, let us look at what are the various types of error configuration you can have. So, for example, you could have a scenario like this. So, you diverge from all 0 state and then you merge back, and at this time instance, let us say your metric corresponding to this path was better than metric corresponding to the all 0 state path. So, you have discarded the all 0 state path and decided in favor of this path. Now, further up, when you came here, you were here, and there was one path which was going like this, and when you came to this time instance t, then again the metric corresponding to this was worse than the metric value corresponding to this path. So, you decided to go for this particular code word, just calling this all 0 state as vector v, code word v, this is code word v dash, and this is code word v double dash. So, the point which I am trying to make is, whenever you have these kinds of multiple error events, you can always upper bound your event probability by error probability of the first event error. So, when you decide in favor of this particular code word, that means this has better metric corresponding to v hat or v, right. So, we can upper bound the probability of event error by first event error probability, and this could have multiple configurations. For example, this is your all 0 state. So, you were here all 0 state, when you came to this point, you notice that this metric was better than this metric. So, you discarded this and you decided in favor of this particular code word, which is your code word v dash, but then when you came here, again this metric was better than this. So, you discarded this and you decided in favor of this. So, this is another way multiple error events can happen, or you could have a situation like this. You are at all 0 state, when you are at this particular instance, you notice this has a better metric. So, you decide in favor of this incorrect path, but then when you reached here, you noticed this path has a better metric. So, you discarded this and then you decided in favor of this. Now, for each of these cases, we can upper bound the event probability by the first event error probability, which we have already computed. So, this event error probability can be upper bounded by the first event error probability. So, we can write a probability of error in this particular fashion. Now, note here you had terms corresponding to various d's. So, you had terms corresponding to d free, d free plus 1, d free plus 2. So, since the value of p is typically very small, the most dominating term in this error probability expression is your first term, which is the d free term. So, you can also approximate your probability of event error by how many such events are there which have paths which have weight d free and this raised to power d free. So, case when p is very small, this bound is dominated by the first term, which is the term corresponding to d free, and in that case we can write down an approximate expression for probability of error like this. Now, can we modify this expression to calculate bit error rate probability? The answer is yes. So, you know what is the weight corresponding to an incorrect path. Now, if we can find out what is the information weight corresponding to these incorrect path, and then we divide it by total number of information bits, we can find out what is the bit error rate probability. So, bit error rate probability can be computed from this first event error probability. This is given by this expression, where BD is the total number of non-zero information bits on all these weight D incorrect paths, divided by k information bits per unit time. So, if we plug that value of bit error rate probability, we can see that we can similarly write the expression for bit error rate probability. It is the bit, this is bit weight enumerating function, and in a minute we will talk about how to generate bit weight enumerating function from input output weight enumerating function or from weight enumerating function. We will talk about this. So, this can be computed from bit weight enumerating function by substituting x equal to this quantity. Okay. Let us just take an example to illustrate this. So, let us consider the same encoder that we have considered. So, it is a 312 convolutional encoder, it is a feed forward encoder, and what is given to us is the crossover probability is 0.01. You are asked to compute what is the event error probability. Now, we know the expression of event error probability, the bound on event error probability, that is given by this expression, and in this particular example p is very small, p is 0.01. So, we can get the approximate expression of event error probability from this. Now, what is the free distance of this convolutional code? Again, if you go back, the minimum weight sequence was 7. So, d free for this particular example was 7. So, free distance was 7 and there was only one such sequence of weight 7. So, we plug those values of d free and a d free in the expression for probability of event error, and we get probability of event error to be roughly 1.2 times 10 to the minus 5. Now, how do we compute the bit error probability? So, first we have to generate bit weight enumerating function. We know how to compute weight enumerating function. It has been explained in lecture 2C. So, assuming you have the weight enumerating function which tells you, and you have the input output weight enumerating function which will tell you what information bit causes, what is the corresponding output weight. So, you could compute bit weight enumerating function by partial derivative of your input output weight enumerating function with respect to w and putting w equal to be 1 and 1 by k times that. If you do that, you will get the expression for bit weight enumerating function. So, for the example that we have considered, we already had the expression of input output weight enumerating function. So, if we plug that in, we get the expression for bit weight enumerating function like this, and then we can divide this by this. So, we will get x7 plus some terms like that. So, in this case also, what is d free? D free is 7 and b d free is also 1. So, this quantity is 1, d free is 7. So, we can approximate the expression, because the first term corresponding to the free distance will be the dominating term. So, we can write probability of bit error to be this. Okay. So, with this I will conclude this discussion on performance analysis of convolutional code over binary symmetric channel. Now, similar analysis can be done for other channels as well. Thank you.